order phase transition. This is definitely first order, and also I don't think you could argue that they have the same purity, the two samples. And another thing that's interesting is that although to some extent the height of this peak depends on how you measure it, so what type of specific heat measurement you do, the single crystals have only ever reached, say, about 8 joules per Kelvin per mole. And this is, quite a big difference between the powders and the crystals. So what causes this difference was the question that we had. And in order to address this, we actually grew a single crystal and then crushed it up. And we crushed it up so that we could compare to a powder sample that had never been grown as a single crystal. And then undertook a fairly careful crystallography study in which we compared the diffraction patterns at 15 Kelvin, so this is in a non-magnetic state, between the two samples. And what we were able to conclude is that the powder sample, which had never been grown as a crystal, has a 0% stuffing, and the single crystals that have been crushed up have about 2.3% stuffing. Okay, what is stuffing? Stuffing is you take an ytterbium ion, an extra one, and put it on the titanium 4+ sublattice, which is supposed to be non-magnetic. For those of you familiar with Herbert-Smithite, this is sort of similar to the case with Herbert-Smithite, where you have extra magnetic ions off of the sublattice that you're interested in, and you're not disrupting the connectivity of the actual power core lattice. So we don't have titanium going back onto the ytterbium site. We only have ytterbium going on to the titanium site. And this is one of the ways that you can have disorder in these floating zone crystals. So how you can determine that you have the stuffing is by looking very carefully at certain relative peak heights. So here, the stoichiometric powder, you have a sort of a lower 222 peak compared to a 311 peak. And then in the crushed single crystal, you see that these peak intensities are almost equal. So that among other peaks in this pattern, tell you sort of about the level of stuffing in your sample. So the question is, in the stoichiometric samples, which are the powder samples, what is the ground state, or what are the magnetic ground state properties? Okay, so that's what the point of this talk is. I think I have enough time. Okay, so we did 2 different neutron scattering measurements on the exact same stoichiometric powder that I just showed you the diffraction from. And in order to make sure that the powder gets cold below 1 Kelvin, it's important to take certain measures. And one of them is you want to use a copper can, and you want to fill it with about 10 atmospheres of helium gas at room temperature. This allows, once the helium goes through a superfluid transition, it allows the superfluid helium to coat the grains of the powder, which actually performs the heat transfer from the copper can. And so without doing this, we know that you won't be able to actually see the signature that we were able to see. And so we did one experiment on the SPIN's triple axis spectrometer at NIST, and that was to measure the elastic scattering in this powder. And then we did another experiment on the disc chopper spectrometer at NIST using exactly the same can. In fact, we didn't open it after the experiment, so should it be exactly the same temperature stability. Elastic scattering. So this is elastic to within plus or minus 0.25 milli-electron volts, which may be an important thing to consider, considering that there is a fair amount of diffuse scattering that we know extends up to about 0.6 milli-electron volts. But within this energy window, what we see is a clear change going from 8 Kelvin to 700 millikelvin to 100 millikelvin on the 111 Bragg peak. So let me remind you that almost every kind of ordering on the power core lattice is Q equals 0, so that magnetic peaks show up on top of nuclear peaks, which actually makes it quite difficult to see them often, especially in a powder sample. So we had to count a lot and be very careful about this. But you can see it even here in the raw data that there is this increase at 111. And taking a difference between 700 millikelvin and 8 Kelvin, there is a peak there, and also at 100 millikelvin minus 8 Kelvin, there's a peak. Similarly, there are other peaks that we measured. We were able to get 5 zone centers, and we could see increases at 111, 113, and 222. So now, let me show you some of the full, I guess you could say, diffraction pattern, except it's elastic scattering, and we selectively picked zone centers here. So we had 5 zone centers. This is at 8 Kelvin, and this is just to show you that this is the same sample that we measured at NPDF on a real powder diffractometer. And you can see the signature of the stoichiometric sample, which is that the 311 is greater than 222. That also persists here. And when you subtract that data from the 100 millikelvin data set, what you see is these peaks that I was mentioning coming up at 111, 113, and 222. But you see a lack of peaks at 002 and 220. So you can actually perform a refilled refinement on this data set, which does include the effect of the error bars associated with the subtraction, which I have not put on this plot because it kind of muddles the plot a little bit. But there are significant error bars here, and that's included in this refinement. Okay, so what we end up with when we do this refinement is that the best fit is the so-called splayed ferromagnetic state, where if you imagine a collinear ferromagnet with all the moments along Z, the crystallographic C-axis, then you cant those moments away by an angle theta, in this case towards the spin ice direction. And that angle we have determined to be 14 degrees plus or minus 5 degrees from this refinement. And the ordered moment is 0.9 Bohr magnetons, plus or minus about 0.1 Bohr magnetons. So the size of the ordered moment is actually fairly consistent with what other people have seen. And the splaying angle, as far as I know, this is one of the first determinations of the splaying angle in ytterbium titanate. Another thing to point out is that this is a long-range ordered structure, at least to within the Q resolution that we have on spins. So we know that the correlation length has to be greater than 80 angstroms. So a natural thing to do